Okay, wait events. So like I was saying, wait events I think is probably one of the most important things when it comes to performance. That's what I'm going to talk about. But I actually titled this talk a little bit differently, and I'm going to step back and start here. I titled this talk, it's maybe a little pretentious, but I called it The Science of Database Performance. And I'm going to start there. Postgres, has been around for a long time. I like this tweet, by the way, from Andy Pavlo. He pulled this quote out of a Stonebreaker history book about this guy in China, Wei Hong, who, if you read this, he was first learning in 1985. He was typing in source code that was essentially the Postgres. It was Ingress at that time. And that was literally how he started learning Postgres. So I mean, like this is one of the cool things about Postgres is you have people who have been working on the concepts and like the way Postgres is architected, it literally goes all the way back to the 80s. Another thing about Postgres, of course, is that thing that people talk about a lot is how it's standards compliant, right? Implements the SQL standard. It's one of the reasons it's a popular migration target from a lot of other databases because of the completeness. But there is something that the SQL standard says nothing about. And what is that? That is performance, database performance. But that's not to say that there hasn't been a whole bunch of like research and thinking in the area of database performance over the last 30 to 40 years, right? In fact, the opposite is true. It's not necessarily something in the SQL standard, but it's something that there is a huge amount of work that has been done and a huge amount of thinking and research and industry stuff to really understand and move forward the field of database performance. Something I kind of like to point out, if you've heard of Brendan Gregg before, he does a lot of really awesome stuff at kind of like operating system, Linux, kernel level. Even Brendan Gregg's like website here, when he talks about the use method, like he says, this might find 85% of issues, but by the way, latency-based methodologies, for example, method R, approach 100%. Method R, if you're not familiar with that, is a database performance methodology. Like even Brendan Gregg and his operating system stuff here is making reference to database performance, the field of database performance analysis, database performance troubleshooting and understanding. So database performance is actually a really sort of rich area to get into. There is a ton of history. There's a ton of really interesting work that's been done here. I'm going to connect that into Postgres in just a moment. But first, a little bit of, I said there's a lot of history. Let's talk about the history. And I think a great way to illustrate the history is sort of like an experience that would be very common for many people who've been around databases for a while. This has certainly been my experience. That I remember back in the 90s. So here we have like a manager might say something like this to me that like, people are talking about this thing called the buffer cache hit ratio. So in the early days of database performances, the first thing that we had was like ratios and metrics and counters. And that was how we kind of started. This is kind of funny. This is actually for real. So let's say manager said to you, all right, I need you to tell me all the databases that have a buffer cache hit ratio less than 90%. So we can, bring in a consultant to work on those. Consultant would do some black magic and, roll some dice, and then he somehow makes things look better. But we kind of wised up after a while to this, by the way. I don't know if you were kind of tracking as this happened, but you can still get this today. If you go out to oracledba.co.uk, look at this right up at the top. Custom hit ratio. Sounds like just the thing I need. The hit ratio is the ratio of how often I'm getting cache hits versus cache misses. And this was like the gold standard for database performance in the 90s, by the way. So I'll pull down this script. Let's see. Here it is. Looks pretty good. People are worrying about hit ratios. Simple routine to bump up your hit ratio to any value desired. Sounds like just the thing I need. Let's see if it works. Choose a hit ratio 85. Look at that. Bam. Hit ratio of 85. Does it work for 90? Yes, it works for 92. Got my hit ratio up where I needed it, and now I don't have to. So this is kind of funny. But it does actually point to sort of a real thing, which is that we started with these, with looking at ratios, looking at like just the CPU usage, the disk I/O, the cache hit ratio, sort of simple counters and metrics. And those aren't bad things, but they're not enough, right? And really, like in the 90s, while all of this was kind of going on in the industry, there actually was a group of people in Redwood Shores who were going very deep on database kernels, who were themselves kind of realizing this same thing, that these were not enough. I kind of highlighted here the time frame, because this was like early 90s, that this group of database kernel developers realized, look, we just don't have the tools that we need with looking at the counter metrics that we're pulling out from the operating system, the database kernel, to really solve the problems that we're running into. So as far back as 1991 and 92, like database kernel developers were starting to think about how we need to instrument this thing and how we need, what we need to add to our code to get the observability that we need to actually be able to solve problems, performance problems. And that was the beginning of something that just continued to gain momentum and gain momentum and gain momentum. They started working on this in the 90s. There's a whole sort of body of work that's grown out of it since then. And I'm not going to go through everything. There's a lot of really good stuff, and I would really encourage anybody. There's so much you can read, and it's, like I said, it's a super fun field to get into of specifically like database performance. But I'm going to highlight two really important things that happened in our industry over the last 15 years. The first one, really important development, was this idea of taking queuing theory and applying it to understanding database performance. And like the hallmark of this is that you see this little formula, R equals S plus W. That stands for response time, service time, and wait time. And I have a couple pages from a book by Kerry Millsap here. He's done a lot of work in this area. Craig Shalhammer is another guy who's done a lot of work. I also kind of referenced him down there. This really kind of changed the game. And I remember kind of like in the early 2000s, as you'd go to like conferences and like listen to what people were talking about, database conferences and things like that, like it all just turned upside down. Like over the course of 5 to 10 years, the whole industry kind of realized that this changed the whole game. There was also an aspect of, this is, by the way, method R. This is the thing that was being referenced by Brendan Gregg at the beginning. There's an aspect of leveraging trace and sort of logging information as well. But the key thing is that the wait time and the queuing theory. The second development I want to really highlight is something called, is basically taking a sampling approach. And these are complementary. They're both important things. So the queuing theory, being able to like generate trace files and then apply queuing theory to the way you interpret those trace files. And the second bit is taking a sampling approach to what's going on inside of your database. This kind of couples. Now, this kind of couples with what went before. I've just kind of pulled a couple of things here. But this, I think that even today, when most people, like, for example, in the Oracle world, when people think of performance, these days, the first thing that comes to mind is like the Enterprise Manager Top Activity View. And the Enterprise Manager Top Activity View is this. It's just a visualization of sample data that's driven off of the $V session view inside of Oracle. So that's what happened in the industry over the last 10 to 20 years. But what about Postgres? How does all of this apply to Postgres? And why am I talking about all that in the context of Postgres? So at this point in time, I have set the stage, and I'm ready to introduce the star of the show. And the star of the show is something we call wait events. So what are wait events? In the so the way the story goes is that I talked about that group of people down in Redwood Shores who were working deep inside the kernel of a relational database, and essentially, the way that I've heard this story is that this was an utter last resort. Like, they had banged their head up against a wall. They could not solve a problem that they were running into. And as essentially, when nothing else worked, they were finally like, okay, fine, we'll add some code to like just log it and trace it and actually figure out what's going on. And they started instrumenting something that are called wait events. Little did they know that those would become the foundation of changing the whole way that we looked at it. So they added some code that could emit log messages when the database was waiting for something, is what they did. One kind of interesting thing, by the way, that, well, I'll probably come back to this later. In 2003, it wasn't until 11 years later that they actually took that wait information and added it to the $session view. That was done in 10GR1. It is kind of funny that in Postgres, we call them wait events, but there's nothing eventful in Postgres. I think this is just ironic. There's nothing eventful in Postgres about how we're exposing it. We're actually, it should have probably been called the wait state. Maybe we'll get to events, though. That's a bit of the history of it. And the thing about wait events is that it's all over these two slides I just showed you a minute ago. So when I talked about queuing theory, right over here, the thing that we're talking about in this formula, the W is for wait. The W is for the wait inside of the wait events. And then when I talked about the sampling approach, and we have this picture here on the right, like those little categories are the wait events. So wait events are all over both of these things that were kind of the fundamental shifts in in the field of database performance analysis. But why are these things called wait events? I have this quote from a book by Gopala Krishnan, but I'm just going to skip that and give you kind of a simpler definition, which is basically anytime the database is not on the CPU, then it's waiting, right? There are some caveats. I'm oversimplifying it a little bit, but I think that it's really important just to have kind of this general concept really solid. I could simplify it even more. I could basically say, look, you have a connection to the database. It's always in one of three states, okay? It's either idle, it's doing nothing, or it's active, meaning it's processing a SQL command. And if it's not idle, it's either on the CPU or it's waiting. I mean, that's just pretty much it. And then the one other thing I would add that really made wait events powerful was that the wait events were visible from SQL. That was the other kind of really, that's something that has really made them, I think, it's enabled us to do so much more with them. And that kind of ties into the sampling stuff. So this is the basic idea behind wait events. What about Postgres? Well, the Postgres community, it's not as though the Postgres community was oblivious to what's been going on. In fact, the first reference that I found was all the way back in 2009, where Itagaki here is talking about profiling, and he's talking about instrumenting wait events in Postgres. That was just the oldest one I found. If you find something older, let me know, because I would really like to update the slide. It could be even before then. But that wasn't the last time. Like, over the following years, just there have been a whole bunch of discussions in the community about wait events, right? I would also like throw on top of that at PGCon in 2015, Ilya gave a talk that was basically all about, again, like sort of talking about performance in Postgres and touching on some of these topics. But that said, as of 2016, the state of the world in the Postgres source code was still this. We had a state which could show us active or idle, but absolutely no sense when a session was active of what was going on. Is it on the CPU? Is it? Well, there was a waiting flag, which would tell us if it was waiting on a lock. But that was it wouldn't really tell us much, and not nearly enough. But that said, at this point in time, the stage was just about set. And in June 22nd of 2015 was when Robert Haas started a conversation with this email right here, which I think is appropriately presented to the hackers list, which is kind of where most of the real technical discussion happens in the Postgres community. And literally within a week, on June 30th, Amit Kapila submitted a patch just for people to start looking at, to start thinking about how could we actually get wait events inside of the database. That went through about 20 versions. There were some challenges I went through, but on right here, on March 10th of 2016, we have the commit, and it came into Postgres version 9.6, where we finally brought in some real wait events, what I would call wait events at least, to Postgres. So the idea was that column called waiting, we replaced that with something a lot more descriptive. That was, in fact, that was the subject line of Robert's original email. I'm not going to go super deep on this. I think this was a really brilliant patch, and the really brilliant thing about it was the simplicity of it. The main patch there, the one on March 10th, was only 800 lines of code. And in 800 lines of code, they were able to instrument all of the heavyweight locks. All the heavyweight, the lightweight locks, and the buffer pins. And then there was additional 200 lines of code when they auto-generated a file, which was sort of setting the groundwork. The reason that's important is that they put that relatively small change into Postgres 9.6, which was a major release of Postgres. And then you could give it some bake time, right? You can kind of see that give it some time to stabilize, get it under some real workloads. And the Postgres tends to develop in this way just as a rule, that Postgres, the development community tends to work iteratively, right? And you can look at a lot of examples of this. Like logical replication is another great example where it's very iterative. They added kind of like the core feature, and then over the years they kind of built it all up. It wasn't a big bang, build everything all at once and ship it all at once. So that was the beginning, and then over the coming year we had a whole bunch of more commits that basically added everything else. So we instrumented everything else in there. There's two sort of key places, if you're curious, that I will point you to, but we won't sort of dwell on it right now, where you could learn more, which is in the source code, pgstat.h is a great kind of starting point to sort of read about how wait events are built in Postgres and where they come from. And the other place is this function called pgreport_wait_start. This is the C function that gets called in order to report a wait event. This, by the way, this is a screenshot of a website called Deoxygen, which is really awesome if you're ever just trying to browse around through the source code, the Postgres source code, because it's all interlinked. So like what you see here is that you pull up this C function, and it tells you all the callers of that C function. And so this very quickly gives you an idea of all the different places where waits can happen, where Postgres can go off of a CPU, at least all the parts unless we missed any. but I think it's pretty good. So here's that same function in the source code. Wait, is this the same one? No, this was the wait start. This is the first one, and then this is get wait event, the second function here. And this is the other good starting point for wait events. This is what translates. So the other thing I would sort of say is that whenever I am curious about a wait event, it's almost always like one specific wait event, because it's the one that's causing a problem for me right now, right? That's usually why I got curious in the first place, because I've got like this problem and I've got a whole bunch of sessions and they say they're waiting for a lock or waiting for something else. And so this is where it does the translation. I've found this to be a good starting point as well for digging into the code. Now, it is worth sort of quickly mentioning that if you come from another database system and then you migrate onto Postgres, there are still some gaps in what Postgres has so far from what you probably had before you came over. I've listed a few of these, it can be useful just to kind of like come in with, sort of know what's going to be there and what's not going to be there as you come over. And so I want to just kind of summarize some of this stuff down. It's just, I do think it's important to get some of this out there to figure out what you can do and what you can't do as you come over to Postgres. So that introduces wait events, but probably the more important and relevant question for most people is, how do I use this thing to actually solve my problems? And so let's spend a little bit of time talking about that, because that's really the important part. And there's basically two levels here I'll talk about. There's sort of the 101 level, undergraduate, then there's like the 401 level, graduate school level of how you use wait events. And the 101, the kind of like obvious thing, the starting point, is that something's going on in my database. Now, wait events are reported in pgstat activity, right? That table, if you're not familiar with it, this is what pgstat activity looks like, all right? It has one row in the table for every connection to your database. If you have a connection, then you have a row in here. And then it shows you stat activity. What's the activity of that connection right now? So in this example, this is from a real system. This was a system that I observed at one point. We have a lot of connections. Looks like there's 33 of them here. Some of them are active, some of them are idle, but they're connected. There's an existing network connection between a client and a server, and there's a back-end process running. So there's a connection. And the first thing you can see is you can see the state. The active ones are pointed out. And the second thing is in this table, we have two columns, and they show you the wait event type and the wait event. So, I mean, the number one simplest way that you use wait events is that something's happening in my database right now. I just look and see what's going on. In this example, we'll see a couple things that we see a lot of. We see some lightweight locks, the buffer I/O lightweight lock, and then we see some guys who are doing I/O. So you see quite a bit of I/O, right? Some of these sessions, there's select statements that are doing a data file read. So that tells you that right now, at this very moment in time, that connection is reading a block off of the disk. That's what he's doing. There's another guy down here. You can see a vacuum process who's on buffer pin. That means he would like to go clean up this buffer, and he's just waiting for everybody else to be finished with that buffer so he can just exclusively grab it for just a moment to really quickly do a bit of cleanup, vacuum it up, and then he'll release it. But he's currently just waiting because somebody else is doing something inside of the block that he wants. So that's the 101 level. Oh, and then I zoomed in a bit just to make it a bit easier to see. I should have gone up to this slide first. One kind of note, this particular issue that I was working on, like these were all, I was specifically looking for long-running sessions. So these 33 were, that's why they have that 2 hours as the transaction runtimes in there. What's the 401 level? The next level of using wait events is to combine wait events with sampling. And this is what I kind of introduced the idea at the beginning. And once you start, so the basic idea behind sampling is like, so I showed you the table, which says right now at this point in time, here's what all the connections are doing. What's really powerful is when you just start like grabbing a picture of that table, like every second, say, or every 10 seconds or 5 seconds. We like to do it every 1 second. It gives you an amazing amount of data. So what it's not doing is generating like a profile or a trace. But what it is doing is just you can infer what the general profile looks like of your connection by just looking. As long as you made sure that every 1 second you took a sample, then if I have a SQL statement that was running for 6 minutes, I'm going to have 600 samples, right, of what it was doing. And and every sample was exactly 1 second spaced apart. So that means that if 500 of those samples are doing I/O, then probably, well, let's see, I said it was 6 minutes. Let's say it was 10 minutes so I can make it a bit easier. If 500 of those samples are doing I/O, then I can safely infer that it was probably doing I/O for 50% of the time. You know, I didn't actually measure exactly when the I/O started and stopped, but it's reasonable that knowing that the samples are representative of all of the time, I can kind of make inferences like that. So once you start collecting that data, you can use very simple analytical queries. And I've got a couple of, there's a whole bunch of approaches that are doing this for you. So the top thing, this is what Performance Insights does. Performance Insights, every 1 second, it directly attaches to memory so that it doesn't have to run SQL. Actually, excuse me, in RDS Postgres, it does use SQL. In Aurora, it directly attaches to memory. And what it does is every second, it just grabs a snapshot of pgstat activity. And it just saves it. It doesn't save it on your database server. It saves it outside somewhere else so that it won't be impactful at all. And then it takes that data and it allows you, it visualizes it, and it gives you a really amazing GUI that you can kind of slice and dice and zoom in and zoom out. There's a couple also, like these tools with something called PG Center, PG Sentinel, PG Weight Sampling are more tools, and there's probably some that I don't even have. If you know of more, I'd love to hear about them. These guys are putting it into more SQL accessible formats. I can kind of summarize what you do with it. This slide is just sort of like showing you, just sort of in SQL, kind of what I was just describing verbally, right? I was saying like that a SQL ran for 10 minutes, right? So this is sort of doing the same sort of thing. It's just, this is here at the top. First of all, I'm just saying, I want to find, I've got all the activity on my system. I want to find like the one SQL statement, which is like putting the most load on the system. Well, load is not the right way to say it. The one SQL statement that's kind of dominating the activity. The SQL statement that's most active on the system. That tells me the SQL statement that my application is waiting for the most. Be another way to phrase that. Well, it's very easy. You just pull all your samples, group by the SQL statement, and count how many samples you had, right? I have all the samples in the system for 10 minutes. Just group by SQL and count them. And if this one SQL had 50,000 samples and nobody else had more than 1,000, well, that one SQL is probably the one I want to be looking at. And then you can drill down even more where you filter now where that SQL is my top problem SQL statement, and then I group by wait event. And now I'm going to see, just for that one SQL, what is he waiting on? Visualizing this another way, this becomes the foundation of the most powerful approach to solving performance problems that I've ever seen anywhere. Partly because it's so simple and because it's so effective. That you can take this simple methodology where basically what you do is you start with your summary of active sessions, start with all that sample data, and then you just find your top SQL and your top wait events from there. And you can do that with SQL. Performance Insights actually makes it really easy to do it visually, so you don't need to write the SQL. But either way works. You just follow the process. Once you have the top SQL and the top wait events, you do an explain analyze with the buffers and the I/O timing, and then whatever other flags you need to see. At that point in time, I mean, it's amazing to me how effective this is, because I've put this into practice dozens and dozens, if not hundreds of times. And almost always it's a very sort of prescriptive, you follow these 3 steps and it will take you straight to the problem very, very quickly, right away. That you can see, you can almost always see exactly what the problem is and what needs to be done to address it. So then the last thing you do, once you have the plan, the execution plan, you can look at the step of the execution plan, which is taking the most time, and you can look at the wait event that's taking the most time. And those 2 pieces of information. So for example, there could be a full scan of a table, and I'm doing a lot of I/O, right? I mean, that just focuses you in on exactly where the time is going, So that summarizes that, but we have a little bit of time left. And since we have a little bit of time left, I think that I could tell you about a really, really interesting development here at Amazon. So doors closed. You guys all seem trustworthy. So last fall, we started, I only just found out about this, all right? So this is top secret, highly classified. Do not tell anybody, all right? But I just found out last fall that, so Postgres is getting really big, right? I mean, it's growing like crazy. And basically, at the absolute highest levels of AWS, we have a complete green light at this point in time to start what we believe is going to be the next huge business, like the biggest thing we've seen, which is selling stuffed elephants. I mean, Postgres is growing so fast. We are going to start a stuffed elephant store. We're going to sell on-demand stuffed elephants, any kind that you want, different kinds of fur, any color, but only blue. And this is going to be huge. We're expecting a ton. I mean, this is gonna explode globally. Global phenomenon here. And this is really great because this gives me a chance. Hang on. Okay, something just flashed up on my screen. And this is not good, but you know what? This is perfect. So this is interesting. I just got this message from Nate. So Nate, I don't know if you've met Nate. He works on the Postgres service team. Also has made some contributions back to the community. Been doing some really cool stuff lately. But he's also been helping to get this Elephant store up and running. But it looks like there's an issue in the dev environment. But this is perfect because you know what we can do here is let's just try out. I've been talking about wait events. Let's try it. Let's just try putting it in practice and see if it works. So let's see here. So wait events. I've been talking about performance insights. I think kind of the easiest way to really get into wait events and illustrate some of this stuff is with PI. So this is what we'll do. We'll use PI. So if you haven't used this before, you start on the console, right? And on the RDS console, Performance Insights is on the left here, fourth one down. So I'm gonna click on the Performance Insights button here, and that takes me here to the PI dashboard. On the dashboard, so Nate said the problem was in the dev environment, so I'm gonna click on my dev database here. And he said, well, there we go. I see something that just ran. So Performance Insights, this is the Performance Insights screen. Now, remember I told you every 1 second, it's taking a snapshot. What it's showing us here is it's showing us what it sees every 1 second. And what it's showing me, and it's stacking up by wait event. So what it's showing me is that starting at about 2:26, all of a sudden there was one active session. So my database it's a dev system, not surprising. It was idle. But then at 2:26, one connection started to process a SQL. And when we looked at it, that guy was blue, and blue is a data file read. So this one connection was reading from a data file for about 2 minutes, and then it looks like it hopped on the CPU twice, but mostly it was reading from a data file, and then it closed. So Nate had said dev environment was slow. Maybe he just, he said search was slow, right? Is what he said. And you know what's interesting? So up at the top here, it shows wait events. But up down at the bottom, it shows you the SQL statements, because it's also grabbing the SQL, right? It's a little bit hard to see because it's low on the screen. But the SQL statement, there's one top SQL statement that's been running in this window. And it says select all of this stuff from the products where the short description is like ? All right, so take note of that. A quick thing, something that I'll tell people sometimes, if you ever work with AWS, as customers work with AWS Support, there's a little gearbox over on the right next to the queries. If you click on that gearbox, let's see here, click on the gearbox, you'll get this, the preferences. You can flip on something called the support ID. And when you flip that on, now it was already down here at the bottom, but now it puts the support ID up. I find that to be a helpful thing. AWS Support cannot see the actual text of SQL queries that the customers run. And that's because there could be customer confidential data in there. It's actually encrypted in such a way that AWS Support couldn't even see those queries if they wanted to, because the encryption keys are not accessible. So in order to be able to help customers, what they did in Performance Insights is that they generate this digest or this hash of the SQL statement, and then they store that in a way that the support can see it. So if you ever do need to work with AWS Support, Support can see, well, there was a SQL doing a lot of I/O and it had this hexadecimal value, but they won't be able to see your actual schema. But now we can go click on that top SQL and we can see, this is interesting. So here's the query, select all stuff from products where description is like % cuddly plush nose %. Well, somebody wanted to find an elephant with a cuddly plush nose. It sounds like a search page though, so I think we're on the right track. Now, the wait event that we saw, the one other thing, like if you hover the mouse over the bar, we're still looking at that light blue, and that was a data file read wait event, right? So what if you don't know, you see a wait event, but you don't know what it means? The place to look, and I will always say this, you always start in the Postgres documentation. I've said that so many times this week already. So let's hop over to the Postgres docs and take a look. This is what the page looks like. Now, data file read is pretty obvious. You probably don't need to look that one up. But you can kind of see, right in the Postgres documentation, there's a wait event table, and it lists out all the different wait events you can get, and it gives you descriptions of what they might be. These are a couple other ones. So to summarize a couple of the things that I just showed you, Performance Insights will quickly give you the ability to see the query text and the wait events by query. It'll give you up to 2 years of history as well. So it's the right starting point. What's the next thing that we do? When I kind of walked through the methodology at the beginning, so now we know the SQL statement. We know it's doing data file reads. The next thing I said was to do an explain plan. If you're not familiar with explain plans, I'll show you. Well, let's just do it. So I'm going to pull up pgadmin, which is kind of a little graphical tool you can use with Postgres databases. You can also do this at a command line with pSQL. And in pgadmin, you can type the SQL, and then you can click on the Explain tab, and it'll show you this graphical sort of visual representation of the plan. Some people like that. Personally, I prefer to work with the text version of plan. So what I'm going to do is put the word explain in front here of the word select. And when I run that, I'm going to get this. So see, I did explain, and I just put like all the options on my explain, like give me all the data. And now what I'm getting is a whole bunch of text down here at the bottom that shows me this is the execution plan for my SQL statement. Now, that works, but there's another trick I'm going to tell you real quick, which is that there's a guy named Hubert Dipez. I can't pronounce his last name, I'm sorry, but the website is Dipez, and he has a fantastic tool that you can use to sort of colorize and visualize your explain plans a little bit. And here, what you can do is just take and copy that text, paste it in, and you will get this right here. So what he's done is it's the same information over on the right, but he just kind of visualizes it a little bit. So what we see is there's kind of 3 steps in this SQL plan, and it's a tree format. So first it's doing a sequential scan of a table, then it's doing a sort, and then there's a limit clause on the top, okay? That's the 3 steps. Now the thing with this visualization tool is that you don't really need to try to read it all, because what he does is he just gives you in bright red where the time went. So all you do here is you just say, where's the red one, which is the bottom one here, 113 seconds in the sequential scan. So that's an important piece of information. We're doing the SQL, and that lines up, right? In the PI chart, it ran for about 2 minutes. We saw data file reads. And here we see 113 seconds in the sequential scan. It also tells us I/O timings. Read equals 111 seconds. So all of this lines up exactly. Now, Nate said he was having problems in the dev environment. What's the sort of obvious thing to do in any situation like this is if I have a QA environment that's working fine and a dev environment that's broken, let's compare, right? Sounds pretty obvious. So let's do that. So now I've connected to the QA environment here, and I'm going to run the same thing. Here's my explain plan. And here's pasted into there. And you see, OK, the red takes me right to the line that spent the most time. But take a look at this, 8 seconds instead of 120 seconds. And look at the plan. If you look at this, it's a different plan. It's got 4 steps. And what's it doing? It's doing an index scan. And then it goes back to the heap, so back to the table after it reads the index. And then it sorts and limits. Oh, we're using an index. Well, that is interesting. Before I go to the next step, let me summarize these 2 bits. So explain plans. This is going to give you the execution plan, which is going to walk you through exactly how Postgres is going to execute your query that you gave it. It'll show you the estimated cost. It can also show you, if you use the keyword analyze, it'll show you the actuals as well. And that's how we've been getting the actual numbers. All right, so we used an index. So let's compare the indexes between our QA and dev environment. We Just select star from pgstat user indexes. Simple way to say list all the indexes where the relation name is product, so on this one table. And if you look here, right off the bat, we see it looks like our dev environment on the left has 4 indexes. Our QA environment has 5. We might have found the problem. System catalogs make this easy, right? You have system catalogs in Postgres that will show you all of the objects. You have statistics views as well that show you the usage of the objects. I don't know if you caught that, but this was also telling us for each index how much those indexes were being used. That's useful as well. How many tuples were read, fetched, that kind of stuff. So easy. All we should have to do is create that index in the dev environment. So let's create the index. With pgadmin, you can do this, where you just sort of right-click and give me a create script. And then we'll run that create index command in our dev environment, and problem did not get solved because it didn't work. Well, this is interesting. I tried to create the index, but I got an error. It says operator class gen trigram ops does not exist. Okay, if you've never seen this before, I know what's going on here. So this operator class, so this is a special index. This is where it's doing a create index, but you see there it says collate pg catalog default, and then it says gen trigram ops on the end. It's that, and that gen trigram ops is using a custom function inside of the index, and that function is something that is defined in an extension. So extensions, if you're not familiar with these, I like to tell people they're like Alexa skills, is what I like to say. It's basically a way that you can give your Postgres database capabilities it didn't have before. Another aspect of that is that there's a handful of extensions, like just a couple that are actually maintained as part of the Postgres project. The vast majority of extensions for Postgres are actually extensions that like other people have made. So the whole like, one of the best things about Postgres is that like forever, it's always, they've had this mentality that we should be extensible. Try to make an extensible database that other people can build things to plug into, which is why I actually think the Alexa illustration is great, because part of the genius of that is that anybody can build new skills and plug them in. Same with Postgres. Anybody can build extensions. And some of the most popular extensions, like, so the geospatial capabilities, Postgres is like famous for having very good geospatial capabilities. Well, actually, Postgres doesn't have geospatial. There's a project called PostGIS, which is an extension, which is a whole different community. Like, it's a whole different group of people, different developers, different committers. They store their source code somewhere else. It's an extension that plugs into Postgres, right? And there's a whole bunch of these. There's lots of extensions, and that's what extensions do. And this, there's an extension here called PG Trigram. Once I create that extension, run my create index, it works fine. And there we are. So now that I've made the index, let's rerun on our dev environment that same plan with, we even put cuddly plush nose right back in there. And if you look down at the bottom, now my query ran in 341 milliseconds instead of 2 minutes. And now I think we can safely say that we've solved our problem. So yeah, Postgres does have a really rich set, by the way, of index types too. That's another thing you really need to dig into if you're coming from another system. Postgres can do a lot more with indexes. And then I talked a bit about extensions already. Extensions are a super important concept, especially too because extensions, you have to install them, just like you have to, plug your skills into your Alexa, right? You have to install an extension in Postgres. You have to upgrade your extensions. They're upgraded separately from the main database. So that covers that. Do we have time? You know what? I just saw one other message flash up, and I think we've got a couple more minutes, and it would be worth taking a look at one more example here. So Grant just sent me this message 5 minutes ago, as you can see, while we were talking. And I glanced at it a moment ago, but he was in a meeting with some top customers about the Elephant Store secret program, some preview customers. And he says that he's heard that for a couple of weeks now, the site gets sluggish on occasion maybe a couple of times a day. It seems to hang for a minute, but they restart their browser and everything is fine. So the customer says it's sluggish, but we asked them if they restarted their browser, and they said after a browser restart, it was fine again. So it's clearly not a database problem, right? Right? Okay. Well, we've been talking about PI. Let's take a look at PI. So this is prod, because these are preview customers on the prod box. So we're going to take a look at our actual production database now. And here's the PI screen from production. And that looks interesting. So that's not what we want to see. The black line, by the way, in Performance Insights tells you the number of physical CPUs you have on your box. In this particular case, these blue spikes are not CPU, so the CPU is always green. So we're not running out of CPU, but it's a really useful calibration point to have. So I do think that's worth kind of highlighting. But we have some big spikes here. It looks like on some kind of a regular interval, I'd say about every 30 minutes, looks like twice an hour-ish, I'm getting this big old spike. Well, we want to look at that. Let's look at that. So Performance Insights, great drag and drop capabilities. So what you can do is just drag with your mouse over one of these spikes. When you do that, it'll zoom in. Another thing about PI is that right now, if you look, we're getting 1 minute. It's showing me a data point for every 1 minute, right? You have to zoom in, and as you zoom in more, it'll get more granular. It does have samples down to the second. So we'll zoom in a bit more. So now that I'm under 5 minutes, it's giving me the 1 second samples. And this is a shape. Zooming in even one more level here. I have seen a shape like this so many times. This is what happens. This is often what broken systems look like. Broken performance systems look like. Super common shape that what you see is this ramp up, and the flat line at the top is when your connection pool maxed out, right? Basically what this means is that for a moment here, literally every single connection from my app to my database was stuck. And it would have kept climbing because, the healthy system, I've got a ton of connections. You can see here, it looks like there's about 32 connections in my pool, right? And on a healthy system, there's 32 connections, but at any given point in time, only 1 or 2 SQL statements running. What happens when you start to see a performance problem is that instead of those SQL statements running, well, one of those SQL statements, like instead of going in a millisecond, suddenly maybe it's stuck, maybe it's not stuck, maybe it's just going to run for 5 minutes and then stop. But even running for 5 minutes can tip over a system completely if all of those are supposed to run in 2 milliseconds. You only have 32 connections in a pool, and if you have like 64 threads in your app, just 32 of those threads have to run the 5-minute SQL, and then bingo, your system is down. You've exhausted your connection pool. And what's happened here is that just something is clearly wrong, right? Because the connections are slowly stacking up, and the system falls over. So what's our wait event here? This is great. Try to reiterate this, that the approach that I've seen be marvelously effective for troubleshooting performance, and this is on, I would say on any database that has wait events, is your starting point should always be the wait events. Start here. It's not that you can't use GDB. Those are all actually really, really crucially important tools. But the reason that I tend to say that this is the starting point is because what I've observed is that the time that it takes you to get from problem to solution can be shortened so much. And I've just seen the vast majority of the time, it shortens the time dramatically to start here. And you just have some key pieces of information that get you to the problem quicker, get you to the solution quicker. So our top wait event here was transaction ID. See that light blue in this case? We look at the key, it says transaction ID. Now we need to look this up. Postgres docs. So transaction ID is in the section, the category that says lock. And what it says, transaction ID, it says it's waiting for a transaction to finish. But this is what I introduced earlier, heavyweight locks. So basically what this means is that all of these sessions are waiting on a heavyweight lock. That's what's going on here. They're all trying to access something which has And transaction ID, this one in particular, you see there's a couple different kinds of heavyweight locks, but the important thing to point out is that this means there's just some sort of a lock on an object which isn't going to be released until the transaction commits or rolls back. And that's what we're looking at. So that's why it says waiting for a transaction to finish. Right? All right, so let's go back to PI. And now let me show you a few more tricks with PI. This is useful stuff. So over here where it says waits, this is actually a drop-down. What we're going to do is click the drop-down. Instead of waits, we're going to pick SQL. So now we can actually slice it by SQL statement instead of wait event. And this is interesting. So now you can drill in, and you can see, by the way, if you didn't realize this, are you looking at your lab environment right now? Yes? Yes? OK, so you guys all connected the dots there. This is your first lab exercise, and you are welcome to do it with me right now, to walk right through this. So you should be able to do all of these same things in your lab environment. So now we're looking at it by SQL statement, and you can see there's one SQL that clearly dominates, and it says update popularity SQL. All right? So the next thing we can do is now notice at the bottom it switched to wait events now, right? So now what we can do is we can do something kind of cool where we select a particular wait event, right? And then we filter on that. Now, the reason I'm doing this is because we had a heavyweight lock, right? All of these sessions here, this SQL statement is waiting for a transaction. The thing that I need to know, oh, they must have had it at 11. The thing that I need to know is who's blocking them, right? So in order to figure out who's blocking them, I need to know who's not waiting. How do I do that? Well, the way that we do that is what I'm going to show you. So we got the SQLs at the top, and what I'm going to do is you notice that somebody is not blocked. Somebody's on the CPU. So what I'm going to do now is click on CPU on the bottom. And when I do that, now it filtered everything out except for the CPU sessions. And up at the top right, you can see the SQL statements. This is only the SQLs that are on the CPU. And now I'm able to see, oh, look, there's this one SQL running this whole time. That seems really suspicious. And that yellow line is select load partner, this guy right here, right? So now I'll click right on that, and that brings me back to this screen. And if you look at the timing, that again, like this looks awfully suspicious. You see this SQL statement starts right here, and then as soon as that SQL statement finishes, what happens? Boop, system clears up. So what we have here is very strong evidence that this is the SQL statement that everybody else was waiting for. He's the one who's probably holding the lock. Now, if you catch something like this in real time, you can query a view PG locks, and you can actually just see directly who's blocking who. The issue for us is that this thing only happens twice an hour, and it was in the past. So you can't look at PG locks from an hour ago. You can only look at it right now. Now, if you were capturing snapshots of it, like I suggested at the beginning, you could, if you're lucky and your snapshot caught this at just the right moment, you'd have it. So let's just zoom in on this particular SQL statement, which is the load partner data function. And this actually turns out to be pretty easy, because the great thing is, if you look here, this is a function which is just running a SQL statement. So now we can just go right back to where we were a moment ago, apply the same process that we were doing before, just do an explain. But this gives me one more thing to highlight. Explain analyze will run the statement. So be careful with that. This is an update statement. So the reason that's important is if I explain analyze update, I'm going to actually update some rows. So what I'm doing here is I'm going to put the word I'm going to wrap it in a transaction and put a rollback at the bottom. See how I did that? And then the other thing to look out for too is if you ever use PG admin, up here at this lightning bolt on the right side, there's a checkbox for auto commit. You want to make sure that it's not auto committing, because then it could just run your SQL and commit it. That's not what we want. We just want to do an explain. So once we have that in order, we do our explain analyze. That pulls, notice up here that pgadmin tells me I'm idle inside a transaction block. That's great. That means it didn't commit. So I'm happy. And then at the bottom, I've got my plan. Put it into deep as, and what do we get here? I love this tool. It brings your eyes right to the step. It's the merge join step. Now this is interesting because you know what a merge join is? So it's where I have two sorted sets of data, and then I'm just merging them together. I read both of them in order, and then I just merge the rows. A merge join should not take 30 seconds when everything else is like lightning fast. So something is sort of fishy about this. Something is fishy here. And I've seen something like this before. So this is a great opportunity to point out. When you see something fishy like this, something to always kind of watch for is what's in your output column here. This is telling you the columns that are being passed up to the next step. And if you look here, there's this one adjust partner popularity, which has a parentheses. That's a function is what that is. So that's a function. So what's going on here is that this SQL statement had a function in it. Let's go back and look again. Yes, look, set view count equals view count plus adjust partner popularity of the subquery count. So that's a function that's getting called. And what's happening is it's calling that function at this step. So for each row, it has to call the function, right? It's quite likely that that function is what's responsible for this 30 seconds of time. So let's take a look at the function and see what we got. Here's the adjust partner popularity function. Well, this is just a PGSQL function, but the great thing about this is that it gives me an opportunity to highlight one more super common thing that we see, which is numeric, the use of a numeric data type. Numeric in Postgres is not the same as numeric in other databases. In Postgres, so in other databases, the numeric data type can have like maybe a couple hundred digits, right? In Postgres, the numeric data type can have up to 16,000 digits after the decimal and 131,000 digits before the decimal. It's probably more than you'll ever need. It's extremely precise. And there's a cost that goes along with that. So the thing to kind of realize with Postgres is that the numeric data type is there for when you need like an awful lot of precision to know that you'll never lose that precision. But there's a computational cost, right? It's just when you're having to deal with that level of detail, it is a bit computationally expensive. So in Postgres, one thing, a general rule of thumb is use the right data types for what you're doing. Postgres has a very rich set of data types available. In Oracle, for example, it's not common to use like an integer data type or a double data type. In Postgres, it is really common to use a big integer, for example. If that fits the range of what you need. A lot of conversion tools don't do this for you automatically, but when you migrate from another database to Oracle, if your numeric already had a constraint that it could never go over 10 digits, then a big int will absolutely work for you. So we'll just do that here. In this particular case, now this is a little contrived, right? I just have a for loop that's adding onto a numeric, but that's okay. This is just an example. So we'll take and rewrite it, and we'll use a big int instead of using a numeric, and then we'll just update our function to look like this, and let's see what happens. Well, once we do that, let's see, did I run this before? I didn't. Once we do that, we can go back to our original SQL statement. Remember the SQL statement that took about, 2 minutes to run? Not 2 minutes. Was it 2 minutes? 7 seconds, not 2 minutes. So it took 7 seconds to run. But if we take a quick look at it now runs in 4 seconds and 708 milliseconds. It sounds better. So let's put that query in to our database and see what happens. Well, I put that query in right around this timestamp of 9:20, and it looks like my spikes disappeared. However, there was one time, this was actually working with somebody in Amazon Retail, with a customer in Amazon Retail one time, that we were troubleshooting a problem, and the problem went away, and we were like, yes, the problem's gone. And then we found out that they had just like stopped scheduling the job, and they had to turn it back on later, but we were like, oh, problem is not solved. So we do want to check that this job didn't just stop running. So what we can do is we can zoom right down to that time window when we expected it to be running, because you see it was on a schedule. And once we kind of zoom in here, take a look at the list of SQL statements that are running, and the one fourth down at the bottom says select load partner data. We can even click right on that SQL statement, and once we select that guy, here we go. We selected him, and now it's showing me just the SQL, and I'm seeing that it ran in 2 seconds, which is about what I expected. So that's another example of using performance insights, in this particular case, heavyweight locking, which turned out to be at the bottom of the issue. And we will leave it here for now. This would be, yeah, we'll leave it here for now. There's more I could talk about. I love talking about wait events, and I love talking about solving performance problems with wait events. And we might dive into some more stuff in the second session. We'll definitely do some labs in this area. But yeah, that said, I always tell people wait events are the best possible place you can start, the best possible starting point for trying to troubleshoot and diagnose performance problems. And this applies to when you're helping people, when you're helping your customers, if you're a consultant helping customers, the same sort of thing there. I spent many years doing that kind of stuff as well, and it was always a sure bet as a good starting point for a performance problem, was to start by looking at the wait events and to look at the sort of sampling-based summary of the system. All right, thank you for coming.